Randomness appears to exist all around us in our everyday lives, from the shape of clouds to hitting that streak of 4 green lights in a row, to flipping a coin and having it land on either heads or tails. However, when we take a closer look, we see how things start turning deterministic, and the question arises whether it is actual randomness or simply an illusion of randomness. In physics, there are these simple equations that allow you to predict the motion of an object as it moves in a parabolic trajectory by knowing only 3 variables. Some more complex equations allowed for Voyager 2 to make flybys of all of the outer planets in a single route. Even things that seem random at first, like the previously mentioned coin flip, can become deterministic by knowing the forces that are applied to the coin when it is getting flipped, allowing you to always be able to ensure the outcome, thus making classical mechanics full of certainty. But sure, the motion of the one might be predictable, but what about the motion of the many? On the large scale, the motion of fluids, whether it is a flow of water or the path of the wind, can be predictable. But what about the individual atoms making up that fluid? Brownian motion, by its very definition, is random. Tracking the position and forces of every atom in a fluid of 2 to the 23 molecules is not exactly the most practical thing, a conclusion which gives rise to statistical mechanics. And just to get a taste of what kind of subject we're talking about here, allow me to read you the opening paragraph of the textbook States of Matter. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. Besides having one of the best openings to any textbook ever, it also contains what I consider to be the most beautiful equation in all of physics. And yes, I do realize that it is a bit of a hot take, but I just find Boltzmann's interpretation of entropy to be an extremely elegant solution. It sets each individual particle to be a microstate, with the combined system forming a macrostate. Each allowed microstate is equally probable. This means that every single macrostate will exist for the same amount of time as any other. However, the most probable states will be the ones that are observed more often. Take a room full of air. It is possible for all the molecules of air to concentrate in one corner of the room, all on their own, since it is one of the possible macrostates. The reason this doesn't happen is because the vast majority of macrostates have the air molecules more or less equally distributed in the room. And since the molecules will go through every macrostate spending an equal amount of time in each one, it results in us always observing the air molecules being distributed throughout the room, as it is the most probable state where the changes between the distributions are so numerous that they simply have more possible macrostates than the extreme ones. However, the system is probabilistic, with the most probable state being represented by this curve that you see, called the Boltzmann distribution, giving you the probability for the energy state of each particle in the system, with the movement of the particles within the fluid causing exchanges of that energy and redistributing it to form this curve. The large number of particles making up the fluid makes the use of probability be due to ignorance of information about each microstate, that is making the predictable macrostate. But of course, that isn't true randomness, since all this represents is our lack of knowledge about the system, resulting in the inability of making accurate predictions. But much like the coin flip, given perfect information, this too will become deterministic, and you are free to accurately predict its complex future. And there it is then. Given that we have all the information about a system, everything about it can be predicted, making randomness only an illusion, meaning that if we just place an object inside a control environment that we know every parameter of, we will know exactly what is going to happen. Right? Schrödinger's cat is one of the most famous thought experiments ever, and I did double check, it was indeed just a thought experiment. It represents how particles can exist in all possible states all at once. It achieved this by placing a cat inside of a closed box with a fully random mechanism that has a 50% chance of killing the cat. Now, you might be thinking that just a minute ago we talked about how probabilities are not actual randomness, and given that all variables are known, then surely the probability becomes 100% of the cat either being dead or alive. So how could it be possible for a trigger mechanism to have an actual random 50% chance? This is where nuclear decay comes into play. Any and all radioactive nuclei have a certain half-life, thus representing the amount of time that it takes for half of the material to undergo nuclear decay. Curium-235, for example, has a half-life of 5 minutes, meaning that if you had 1000 Curium-235 atoms, only 500 of them would remain after 5 minutes of waiting. In other words, by just having one Curium-235 atom, after 5 minutes it has a 50% chance of decaying. Okay, that is good and all, we can measure the decrease in radioactivity and therefore know the half-lives. But what makes these probabilities different from the ones in statistical mechanics? Well, it comes down to the process of nuclear decay itself. The nucleus of a radioactive element is unstable, and in order for it to become more stable with a lower energy state, it has to lose some of its protons, as their ratio to neutrons is too high, resulting in the electrostatic repulsion between the protons trying to rip the nucleus apart. But the strong nuclear force holding them together is still much too strong, and yet every now and then alpha decay happens, meaning that an alpha particle or helium nucleus gets ejected from the parent nucleus to bring the ratio of protons to neutrons to a more stable configuration. And the reason as to why this process is truly random is because it requires for the alpha particle to teleport through a wall. Quantum tunneling is a consequence of the wave function, which can be thought of just like the electron cloud around a nucleus, as it tells you the probability of the particle being in that position at any given time. By looking at a space from negative infinity to positive infinity, the wave function becomes 1, meaning that the particle exists somewhere within that space. Of course, we want a bit more precision than that, and we can look in more specific areas or even close off the rest of the possibilities by placing barriers. You can think of the particle as a ball bouncing between two walls, with the wave function only showing the probability of finding it in each position given that we make an observation of it. But the wave function doesn't drop to 0 when it meets the wall. You can think of it as how sound can leak through a room, with the door and windows closed and the walls insulated, but still a little bit of sound will still be able to make it through. When the wave function reaches the barrier, it starts to diminish exponentially, but given a relatively small distance, it means that a small fraction of it is able to leak through, thus allowing the probability for the particle to exist in that space. And with enough time given, it allows for the particle to teleport through that wall and onto the other side. Exactly what an alpha particle has to do to escape the strong nuclear force holding it in place. But how do we know that the wave function isn't just like the Boltzmann distribution, probabilistic due to lack of information, but not actually random? Even if the two graphs may look similar, the difference arrives at how they are created. A Boltzmann distribution shows particles moving between microstates, with that movement being determined by parameters that when they are hidden makes these movements appear as random, and when they are known it makes the movements deterministic, with the use of probabilities being there due to our lack of knowing of the values for those parameters. Whereas a wave function shows the probability of a particle in a position, but this time there is no hidden variables that can make that position deterministic. Instead, the particle is in superposition of possible states until a measurement forces it into a specific outcome. But how do we know that there are no local hidden variables determining that outcome? To put it simply, it is because experimentally quanta break Bell's inequalities. Imagine 4 boxes, each having 120 colored marbles inside of them. 2 of them have an equal number of red, blue and green. As for the other 2, we'll get to them in a moment. Of course, you cannot see inside those 2 boxes, but you go and pick 1 marble from box A and then 1 from box B. Note down their colors and return them back to their respective box. Then shake the boxes and you go all over again. After enough tests, you expect to find that the marbles match in color 1/3 of the time. Since each color has a 1/3 chance of being picked and the boxes are independent of each other, it means that 1/9 of the time you will get both being red, 1/9 both being blue and 1/9 both being green. So overall, matching in color 1/3 of the time. Now we move on to the second set of boxes. Much like the first pair, you cannot see inside of the boxes, but you go and you pick 1 marble from each one, and note down their color and return them back to their box. And after many tests, you see that this time the chance of picking red from box C is 1/3, just like it was before with box A, but then the chance of picking a red from the second box is not 1/3, but instead 3/4. That's fine though, it can be easily explained by having the second box not have an equal number of all 3 colors, but instead be made up of 80% reds. However, another measurement that you have made is that when a green is picked from box C, which also happens to be 1/3 of the time, there is a 3/4 chance that a green is picked from box D, which can only be explained by having box D be 80% made up of greens. But of course that conflicts with the red measurement, and the numbers exceed 100%, which cannot be, meaning that no configuration of box D can satisfy these correlations at once. These are exactly the kind of correlations that appear in quantum entanglement experiments, correlations much stronger than any classical deterministic system could produce. The key point is that because no deterministic assignment of marbles can explain these correlations, the outcome of each individual draw is fundamentally unpredictable. Each marble pulled is truly random, even though the overall correlations are precise. Many experiments have this to be the case, and therefore making quantum mechanics indeterminate when it comes to local hidden variables. There are some interpretations of quantum mechanics that allow for determinism to exist, such as the many worlds hypothesis, stating that the probabilistic nature represents different realities that emerge once the measurement is made, meaning that in our universe, the outcome that was produced had been already determined. Or the known local hidden variables hypothesis, stating that there are variables that determine the outcome, but their influence takes place at speeds that are higher than the speed of light. So it would seem that resulting in any possibility for randomness to actually exist, it will have to do with the weird nature of quanta. But perhaps there is one way of making even the deterministic classical physics also random. The n-body problem is one of the most famous examples of chaos theory. What you see here is a magnetic pendulum and 3 magnets placed equally from the center. Each color represents a magnet, and the pattern of these colors represents which of the 3 magnets the pendulum will end up being over if it started from that position. As you can see, the area near the magnets results in quite predictable outcomes. However, as you get further away, which of the 3 magnets the pendulum will stop over becomes far more chaotic. But still, chaos does not mean randomness, and very clearly, as you can see, even though the pattern is messy, it can still be mapped, and given that we know the exact initial position of the pendulum, we can still know on which of the magnets it will land on. But what happens when the scale is enlarged? Planetary motion and astrodynamics in general can be considered quite a certain science. Just looking at the example from the beginning of the video with the whole Voyager mission, clearly indicating certainty. But the solar system is still a 9-body system, and so the predictability in near terms can be very precise, but as time goes on, it leads to uncertainty increasing. It results in the inability to make accurate predictions of the state of the solar system after about 100 million years. This can be best seen by once again using the magnetic pendulum. The messy section can represent the far future, and as you can see, even a slight change in position can completely change the outcome. And this represents a 3-body problem. Imagine the nuance for a 9-body problem. But you can argue that planets are not like points on a piece of paper. They are giant, and therefore the accuracy of their exact position is much greater, with the errors being extremely small, which is true. However, every inaccuracy in the initial position, even at the scale of micrometers, is carried over the course of 100 million years, letting the relatively negligible error grow exponentially, to such an extent that it makes it impossible to create reliable predictions. Okay then, so practically it is not possible, but that is what we said about Brownian motion, and yet at the end of the day it is not real randomness, therefore neither should this one be. If we assume infinite accuracy for our measurements, then it can become deterministic for any length of time. But here comes the problem. Infinitely accurate measurements are not possible. And I don't mean that in the practical term, we are way past that by now. I mean it in the sense that nature itself doesn't allow for it to happen. Heisenberg's uncertainty principle tells us that the precision between knowing the position and momentum of a particle is at an inequality, meaning that the more certain you become of one, the less certain you become of the other, and vice versa. This doesn't allow for the precise measurement of an object's position to the degree needed in order for the error to become zero, and therefore make the system fully predictable towards infinity, resulting in error always existing no matter what, as nature itself cannot know the precise position of an object to that degree, making long-term randomness an inevitable consequence even for deterministic systems. And as a fun side note, this inequality also means that classical particles do not exist, since the position delta x can never be zero, as it would break the inequality. In conclusion, does randomness truly exist? Yes, but it seems to only do so at the scales of the extremely small in space and extremely far in time.